So, calculus is a very powerful tool developed initially by Newton and Leibniz. There are loads of applications that we can see in our everyday lives. So, for if you're in a room and you turn the AC on and you look at the thermometer, it will take some time for it to go up, and you could analyze how is that temperature changing with time. That could be seen as a change in temperature over time. So that's a derivative. Now, let's say that, I don't know, you've got a practical experiment and you've got a bottle with some water inside and you pierce a hole in it. So water will start to leak. At first, since there's a lot of water inside, a lot of water will leak at a certain time. And when water is very low, you only have a very small amount of water flowing. So if you analyze how the mass or the flow or the volume is changing with time, that's also a rate of change. This we could call, for example, a flow rate, since it's a volume per time. Or if we measure the mass instead, we would have a mass rate. And obviously units here could vary from, for example, cubic meters per hour, or cubic meters per second, cubic meters per minute, cubic centimeters per minute, per hour. Depends on the units which are working, right? Depends on how large things are or how small they are. Now also, let's say that you buy some stocks and you analyze the stock market. So if you look at those prices, you can also analyze how is your, well, money or value changing with time as well. So many of those examples, they are things that are changing with time, but you could have things changing with other things as well. It doesn't have necessarily to be time, but time is something very useful for us, and that is useful for us to notice as well. So let's take a look at a few numeric examples. So let's say that we've got an equation that describes the amount of water in a pool in after a certain time. It's draining the pool, and this is the equation that gives us how much water is left. So first question is, what is the average rate at which the water leaves the pool in the first 5 minutes? And letter B, what is the instantaneous rate at which the water is leaving at t equals 5? So one is the average, one is the instantaneous rate. Again, just like before, average, we just take 2 points, we calculate the difference, rise over run, that's a gradient. Instantaneous rate, that's our derivative. So let's do it. Well, for letter A, we just need to calculate what is our volume when time equals 0 and what is our volume when time equals 5. So when time is equal to 0, our equation will 0 this time here, so that's 200 times 50 squared, right? This should be 200 times 5 times 5, 25, 2,500. If we multiply those, we're going to get 0, 0, 0, 0, 25 times 2, 50. So 50,000. We're not told the units here, but I'm going to tell you that this is liters, just so we have something. So 500,000 liters. Now, what about when time is equal to 5 minutes? Well, that's 200 times, and inside of here now, we're going to have 50 minus 5 squared. So that's 200 times 45 squared. So this is 200 times 2025 liters, and that should be, so this is 405,000 liters. To calculate the average rate, we just need to do the difference and divide by the difference in time. So it should be V5, which is the last one, minus V0. This is the average rate. So V5 minus V0 over 5 minus 0. So the difference here is going to be 95,000 liters and 5 minutes. So if we divide those, 19 18,000 liters per minute. Now for letter B, we need to do our derivative. So let's do it here. What would be V dash? So this is dV dt, right? That's the change of volume with time. Let me just write it here to make sure. So this is dV dt. That's the derivative of volume in time, which is the same thing as V dash. Alright, this is constant, so it doesn't change. And then we have something here that has a t inside. So we will have to differentiate this, right? So assume that this is an unknown, like a, right? Make the differential, so derivative of this with a, that's 2 times 50 minus t, and then make the derivative of what's inside, which is minus 1. We can see that this is going to be a negative value, and that just shows us that it's decreasing, right? The values are decreasing. So let's work this out. 200 times 2, that's 400 times 50 minus t, and minus 1. So those are going to flip here. T minus 50. And we can just expand. So that's 400 times t minus 20,000 liters per minute. That's the unit that we're working with here. Alright, so this is our function of time of our rate, instantaneous rate. So now all we have to do is, what is v dash? So what is the derivative of v in time when time is equal to 5? So we just plug 5 here. So that's 400 times 5 minus 50. So that's negative 45 times 400. This will be a negative value, and that's expected because the volume is decreasing. So 45 times 400, so that's negative 18,000 liters per minute. Now there's just one thing here, average rates. The volume here in the beginning was the larger one, so this is in fact negative. It's missing the sign here, and this negative sign means it's decreasing. The rate is decreasing, right? The volume is decreasing with time, and that's why it's negative. We can also compare those values and check that this estimate by using the average is, well, not that far from just taking the value, the instantaneous one at 0.5. So we're not that far. Doesn't look that far. Now let's say that some of you guys are building a company, and you go to Shark Tank, and you have to provide some evidence of some of the numbers that you have. And this is actually the equation given by, I don't know, your financing department, your treasury department, right, of how much you actually need to produce some of the stuff that you're selling. Okay, dollars. So 0.0003 x to the power 3 plus 002 x squared plus 4x plus 2,250. So the first thing that you could be asked is, what is C dash, right? How does because here x is the number of pieces you produce. So let's say that you're producing, I don't know, some nice food for pets. I actually saw the other day some guy selling food for snakes and lizards, and he sold like insects and such. So let's say that this is how many packs, or well, whatever, okay, how many things you're producing. So one thing that you could be asked is, how is your cost changing as you produce more and more pieces? Because what you want, in fact, is to have the lowest cost and to be able to produce the most pieces, because the lowest cost with the most pieces will give you the highest profit. It would be a max or a min of a function. So if we take the derivative here, what would it be? So derivative of cost according to x? Well, let's differentiate this. So 3x squared times 0.0003, oh, I'm missing a 3 here, a 0, 0.03 plus 2 times 0.02x plus 4. And there we go, we've got a quadratic here, right? 0.0009 x squared plus 0.04 x plus 4. And then it's beyond the purpose of this, but if you follow through this, it will give you how is your cost changing as you produce more pieces, more or less pieces, as you change the number of pieces. So that's actually quite simple, right? The concept is quite simple. So if you solve this quadratic, you would find, for example, some max. If you make this equal to 0, you can find exactly how is your cost not changing. When is the point that your cost stops changing? So just to make things a bit more interesting, I am going to plot the graph of this function, and let's see how it looks like. So let's put our function here, 0.0009 x squared plus 0.04 x plus 4. And if we draw it, let's try and find it. There you go. Let's adjust our window. There you go. And let me just move a bit. Yeah, it seems alright. Now let's trace it. I want to find the bottom point. So yeah, we can see that it's around here, right? That's where it gets to the lowest point and then it flips. We can see exactly actually the same value here, this same value here. This is our bottom point. Now just remember that you can always use your graphical solver here, F5, and just click on min, and it's going to find the minimum of your function straight away. So take a look. When you're producing 22.2 units, that would be the point where your cost stops changing, minus 22.22 units, right? That's where your cost would stop changing. It doesn't make much sense when we're talking about money, because then you would need that you only have costs increasing, so there's not much maths to be done here. But if this quadratic was on the positive side here, then we would have a point at which the cost gets less, 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 and less. And then when you see this flipping, it means that for you to produce more items, you would now need to increase the cost. So you're making less profit. So there is a maximum amount, or let's say an optimized amount of units that you should make for you to have the hugest profit.